Hey guys, it's Shiran, and today's video is going to be about a very important graph algorithm called Dijkstra. We're going to learn when to use Dijkstra, so how to recognize problems that could be solved with Dijkstra. We'll learn how Dijkstra works with pseudocode, actual code, and an example walkthrough. And then finally, we'll do a time and space complexity analysis. By the way, in the next video, we're going to use what we learned in this one to solve two different LeetCode questions. So if you're interested in that, go ahead and subscribe. So let's get straight into it. Dijkstra's algorithm is used to find the shortest path from a single source node to all the other nodes in the graph. The most popular example use case is that we have n cities and we have distances between the cities, and we want to find the shortest path from single city to all the other cities. We can also use Dijkstra to solve the simpler problem of finding the shortest path from a single source to a single target. But some questions or use cases don't fit perfectly into the shortest path template, and still we can use Dijkstra to solve them by applying just a few small modifications on the original algorithm. And this is where things get interesting. If the problem can be represented as a weighted graph, either directed or undirected, and you are asked to return the path with the lowest cost, then you should consider Dijkstra. Now the cost can be anything. It can be the sum of weights like in obvious shortest path problems, but it can also be the product of weights or the maximum weight in the path, or any other creative definition you can think of. The only restriction for using Dijkstra is that the cost has to be non-decreasing, meaning the cost of a path cannot become smaller when we add an edge to it. In plain shortest path problems, the cost is defined as the sum of weights included in the path, right? So the only way this cost will be non-decreasing is if all the weights are larger or equal to 0. Because if we had an edge with a negative weight, adding it to a path would decrease its cost, which is what we're trying to avoid. If there are negative weights, we have to consider a different algorithm like Bellman and Ford. Now let's see how the algorithm works. So Dijkstra is a greedy algorithm. It means that at each step, we choose the best option based only on the information that we have at that point in time. We never go back and change past decisions like we do in backtracking, for example. We make the decision with the most immediate benefit and move on without ever second guessing it. So the algorithm works like this. We first create a mini heap of pairs where each pair consists of a node and its distance from the source. The heap sorting criteria will be the distance. Then we initialize 3 arrays. First one is dist, which will hold for each node the best distance that we have found so far. Second one is prev, which will hold for each node the node that precedes it in the best path that we have found so far. And the third one is visited, which we'll use to mark visited nodes. Now, we know that the distance of the source from itself would be 0, obviously. So we record that in the dist array and we push the source with its distance to the heap. Now we get to the main loop, and the main loop actually looks a lot like simple BFS, where you replace the queue with a heap. While the heap is not empty, we pop the node with the smallest distance. This is the greedy part. We want the best immediate benefit, so we pop the node that is closest to the source. If this happens to be a node that we have visited already, we ignore it and continue to the next iteration. If it's an unvisited node, we mark it as visited and look at its neighbors. If we chose to link this neighbor to the current node, the new distance of the neighbor from the source would be the distance of the current node plus the weight of the edge that connects the current node to this neighbor, right? If this neighbor has not been visited yet and this new distance is better than the one we found already, then it means that we just found a better path for this node. So we update the dist and prev arrays and we push it to the heap with its new distance for further exploration. And this is how we keep track of the best distances for each node, by updating the dist and prev arrays every time we find a better option. And that is pretty much the whole thing. When we exit the loop, the minimum distance to each node will be in the dist array. Now, if you're only interested in the shortest distance to a single target node, we can just stop the algorithm once the target node has been popped off the heap here. It is guaranteed that at the point where a node is popped off the heap for the first time, we already have the best global optimal distance for it in the dist array. So we're okay breaking from the loop once we pop the target node for the first time. Now, if you want the actual sequence of nodes and not just the distance, we can construct it by traversing the prev array backwards. The pseudocode will look like this. If you don't quite see it, you will when we do an example walkthrough. Nothing makes an algorithm clearer in our heads better than a step-by-step example walkthrough. So we'll do that next. So we have this example graph and we want to find the shortest distance from this source node, node 1, to all the other nodes in the graph. After the initialization step, we're going to have these 3 arrays. The dist array will be initialized to infinity, the prev array will be initialized to undefined, and the visited array will be initialized to false. And first thing we do is update the distance of the source, and obviously the distance of the source from itself would be 0, so we update that in the dist array. And we also want to insert the source to the heap. And now we get to the main loop, and the main loop looks like this. We first check that the main heap is not empty, and it is not. We have this one element in the heap. So we move on to the next line of code, which is to pop the pair with the minimum distance. Again, we only have this one element, so we pop it. And that makes the cur node 1 and the cur dist 0. And we move on to the next line of code. We check if cur node has been visited already. And to do that, we look at the visited array. And we see that it has not been visited yet. So we move on to the next line, which is to mark the cur node as visited. And next, we want to look at the cur node's neighbors. The neighbors are node 2, node 3, and node 4. We're going to start with node 2. The new distance for node 2 would be the current distance, which is 0, plus the weight of the edge that connects the cur node to node 2, so this edge. So 0 plus 7 would be 0, and that will be the next distance for node 2. Now we check if node 2 has been visited. It has not. And that next dist is less than the distance we have found already for node 2. In this case, yes, 7 is less than infinity. So we move to the next line of code here. To update the dist array for node 2, instead of infinity, we'll put 7. And to update the prev array, instead of undefined, it would be 1 for the current node. Next line is to push node 2 and its distance to the heap. And then we move to the next neighbor, node 3. The next distance for node 3 would be the current distance, which is 0, plus the edge that connects node 1 to node 3, this one. So 0 plus 9 is 9. We check if node 3 has been visited. It has not been visited yet. And if next dist is less than the distance we have found already for node 3. And in this case, 9 is less than infinity, so we update the dist array and also the prev array. We also push node 3 to the heap with its new distance and move to the next neighbor of node 1. That will be node 4. The next distance for node 4 would be the current distance, which is 0, plus the weight of the edge that connects node 1 to node 4. So this one, 0 plus 14 is 14. We check if node 4 has been visited yet. It has not been visited yet. And if next distance is less than the distance we have found for node 4, 14 is less than infinity, so we update the dist array and also the prev array. Next, we push node 4 to the heap with its new distance. And with no more neighbors to go, we move on to the next iteration of the loop. We check again if the min heap is not empty. It is not. We have 3 elements. So we move on to the next line of code, which is to pop the pair with the minimum distance. 7 is the minimum distance, so we pop this pair. We check if node 2 has been visited. It is not. So we move to the next line, which is to mark it as visited. And we look at its neighbors. The neighbors of node 2 is only node 3. So next node is 3. Next distance for node 3 would be the current distance, which is 7, plus the weight of the edge that connects node 2 to node 3, that is this edge. We get 7 plus 10, that is 17. And we check if node 3 has been visited yet. No, it is not. 17 is not less than 9. So we move on to the next iteration without doing any updates. We pop the pair with the minimum distance. This time it's node 3 with distance 9. We check if node 3 has been visited. It has not been visited yet. So we mark it as visited and look at its neighbors. The neighbors of node 3 is only node 4. So next node is going to be node 4. And the next distance for node 4 would be the current distance, which is 9, plus the weight of the edge that connects node 3 to node 4. That will be this edge. So we have 9 plus 2, that is 11. And we check if node 4 has been visited already. It has not been visited already. And if its next dist is less than the distance we have for it, 11 is less than 14. So we update the dist array and the prev array and push node 4 to the heap with its new distance and move to the next iteration. We pop the pair with the minimum distance. That would be node 4 with distance 11. We check if node 4 has been visited. It has not. So we mark it as visited and look at its neighbors. Node 4 has no neighbors, so we move on to the next iteration. The heap is not empty, so we pop the pair with the minimum distance. This time it would be node 4 with distance 14. We check if node 4 has been visited, and it has been visited, so we move on to the next iteration. But this time the min heap is empty, so we exit the loop. And now what we have in this dist array is the shortest distance from the source to each one of the other nodes. You can see that for node 2, it is this path here. For node 3, it is this one. And for node 4, it is this one. Now I want to write the code for this, and the translation from pseudocode to real code is going to be very straightforward. I'm going to use C++, but this is just syntax. You'll be able to follow in any language. And I suggest you code this yourself in whatever language you want. You'll be able to use this code to solve a variety of different questions. So I prepared a little driver program with a few test cases. There's a graph implementation here that uses an adjacency list, and a few helper functions for printing and testing. And I pasted the pseudocode here so we can easily just translate it line by line. And first thing we do is create a min heap. In C++, we do it with a priority queue. And we want each element to be a pair that consists of a node and its distance. Both are integer types. In C++, I would also need to define the container type, and the sorting criteria will be this. And this is just long syntax for defining a min heap of pairs that is sorted by the first element of each pair. To make this a bit prettier, let's move it to a type def, and now we can just declare a min heap type like this. Now let's initialize the three arrays. This one to int max, that would represent infinity. This one to -1, which will represent undefined because our nodes are labeled from 1 to n. And this one will initialize to false because none of the arrays are visited yet. The loop translation is pretty straightforward. It's just a matter of syntax. So we'll do this. Our graph is implemented with an adjacency list, so this is how we would iterate the neighbors. And that is the whole thing. So if we want to also implement the single target version, let's copy the Dijkstra function. This version will also need to accept the target node. And we just need to add this line. And because we're interested in a single target and not all of them, we don't need to return an array of distances. We just need to return one integer, which is the distance of the target node. Okay, let's run this. So we passed my small collection of test cases, so I assume I didn't make any stupid mistakes. But you'll be able to see this code in action in the next video when we'll use it to solve two different LeetCode questions. Now let's move on to the complexity analysis. Let's start with the space complexity. So if V stands for the number of nodes in the graph and E stands for the number of edges, the dis and priv arrays will use O of V space because there's a cell for each node, right? Now we also have this heap, and we push to the heap in this line. And each node might be pushed to the heap once per each one of its incoming edges. So in total, the heap uses O of E space, which makes our space complexity O of V plus E. Now for the time complexity, as we just said, there are O of E push operations, and each push operation takes log of size of the heap, and the size of the heap is O of E. So we get O of E log E for this part. And we also have this initialization part that takes O of V. So in total, we get O of V plus E log E. Now I want to make a few side comments. You might have read that the heap size in Dijkstra is O of V and not O of E. And that makes the time complexity O of V plus E log V. I don't want to get into too much detail, but the way you get this complexity is by using a modified heap implementation that also has an efficient update operation. Off-the-shelf min heaps only have push, get min, and pop min operations that do not have an update operation. The additional update operation would allow us to push each node exactly one time, and then when we need to update its distance in the heap instead of pushing a new copy of it like we did here. And this would have limited the heap size to the number of nodes instead of the number of edges. But because standard implementations of heaps don't include this operation, we didn't use it here. So we get slightly different numbers, but it's not a big deal, just something to be aware of. So let me know in the comments if you like this video and if you have any questions or requests. Thank you for watching, and I will see you next time.